So, well, in a minute. Hang on, it's this question here. What is p-value? Okay. When do we reject a null hypothesis versus failing to reject a null hypothesis? Remind me what a p-value is again. On your quiz, you had to interpret a p-value. Many of you couldn't do that. How do I interpret a p-value? What is it?
P-value is
0.00545? 545, which is greater than 0.05. Oh, you shouldn't. The textbook is wrong if that's the case. But let me double check. In 13, I got two-tailed test 0.054, which is greater. Which means that it says reject. No, you don't. It's fail to reject. Thank you. That's a typo in the book. Okay.
They do it like a lot. Yeah.
When you have a small p-value, I'm sorry, that's a not a small p-value. So for example, in this case, you had 0.0545. That is not, well, we'll say it this way. We want it to be less than 0.05, but it's not. Therefore, we can't do anything. We don't have evidence to reject anything. We have to fail to reject the null. We just don't have enough evidence. Now, the book might be using 0.1 as a confidence level, like a 90% confidence level. In that case, we would reject it. Remember, we only use this 0.05, this alpha level, if none was given. So let's see if one was given in the problem, because if it was, then we could definitely, that would change some things. Oh, it isn't, okay? So it just depends, right? So for us, we're going to use 0.05, which corresponds to a 95% confidence interval, correct? So that means that we have to compare it to that. We want it to be less. It's not here. Therefore, we can't do anything. And we don't have evidence to do anything. Okay? If we have evidence, for example, if we had something like this, that's definitely less than 0.05. That, to me, means we're going to reject that null hypothesis. That means that the probability my sample happened by chance is 0.0005, which means that it didn't happen by chance, right? Which means I can reject that null, which means my alternative is going to be we have evidence to suggest the alternative has some worth. Okay? So thank you for pointing that out in the book. That's definitely a mistake. The only thing where that we could reject it is if we were doing it at a 0.1 level, which is a common one to do. 0.1, 0.05, and 0.01. Remember, 95, 99, and 90% confidence intervals are the common intervals. So sometimes you do, but this is the default. And they didn't give you any evidence to suggest otherwise in the problem. So good point. Thank you for pointing that out. Okay? Now, there's nowhere on this board here, is there an interpretation of a p-value? Nowhere. When I asked you on your quiz to interpret a p-value, several of you wrote this statement. That's not an interpretation. Okay? That would be something we would have to say as part of our conclusion, right? But what's an interpretation of a p-value? What is that? Kyle, you want to give it a shot? Of what? Don't say it. There is sampling variability. When you take a sample, there's variations amongst samples, right? And you can get a strange sample every once in a while, right? And so what's the likelihood that this sample was one of those odd kind of strange samples? That's what that's what a p-value is finding. And we want it to be small because we want that p-value to be really small, which means that the likelihood that this sample happened being so odd and different by just variability is very small. It happened because there is a change, okay? And that's why. Yes, no, maybe so? Sure. All right, so I want to talk a little bit today about this before we jump into the newer stuff. So often, and I'm guilty of this, when I do a hypothesis test, I skip the test statistic. What is the significance? I hate that word, but what does a test statistic do? What is it used for? It is a z-score. That's what, in a one proportion z test, that's what the test statistic is. And let's remind ourselves what the formula is, because a lot of you had it backwards on your quiz. Not over n, but it's over the standard deviation of p hat. Okay? So it's your statistic minus your parameter over the standard deviation of that statistic. All right? So a lot of you had the numerator backwards, FYI. Okay? So let me give you, let's look at one of the problems you did for homework. Let's look at, I don't care, let's look at 13. I'm fine with that. Look at your 13 homework problem. Okay, so in problem number 13, what z-score did we have? For number 13. Well, let me just draw it, first of all. What goes in the middle of the, what was the claim again? 0.34. Our sample was 0.33, right? Because if you look back at our hypotheses here, we had a two-tailed hypothesis, which means that we're going to have something over here as well. And we're looking at finding the probability of the two tails happening. Hunter. In this particular case, you had to do, I'm just showing you the two-tailed test, what it would look like in terms of the curve. But the test statistic means what z-score is associated with that. Do we expect it to be negative? Why? Because it's left of the median, or left of the mean, left of the center, right? So we expected it to be negative. Let's just kind of make sure we understand the formula. So it's going to be 0.33 minus 0.34 divided by, and the square root of, because that's the standard deviation, right? And I think it was 0.34, 0.46 over 8,302. Oh, sorry, 66, thank you. 8,304? 2, okay. So that's the formula that you would be using, okay? And then we would approximate that, and you'd find the z-score to be negative 1.92. Do you guys get that? So when we looked at this particular problem, we compared the p-value to 0.05, the p to alpha, to draw our conclusion. My question is, how can this test statistic also help us draw a conclusion? Because it can. Okay? We can actually compare this to the corresponding z star. By the way, if this is negative 1.92 over here on the left-hand side, isn't positive 1.92 on the right-hand side? You agree so far? Okay, good. So how can I look at those z's, and I want to compare my z to a z star? What z star is associated with this problem? What is z star again? The critical value of z. What is that? Who remembers? What is it associated with? Is it a confidence interval or a hypothesis test? It's a confidence interval. It's what we usually use critical values of z for. Just like we had to assume 0.05 as our alpha here, What does an alpha of 0.05 correspond to with a critical z? What kind of a confidence level would it be? 95%, okay? So 95% confidence is kind of like our default, so to speak. What z star value is associated with 95%? What is it? Nope. 1.96. Okay? If you have 95 in the middle, you have 0.025 on either tail, you want to find the z star associated with that. Inverse norm. This is what we had to do before. Okay, so if I do inverse norm of 0.975, because we're including one of the tails, you should get 1.96. Okay? So the z star is 1.96. The actual z using our information is 1.92. What's the problem here? You're going to compare those two things. They're pretty close, aren't they? Aren't they? These were pretty close, weren't they? This one was bigger. This one is not. Most of the time, and when you have a one-tailed test, one-tailed, this is not a one-tailed, it's a two-tailed, you are going to compare your z to your z star. You want it to be less, and it is here. But what's the problem? Mm-hmm. Right. Why? It's a two-tailed test. Didn't we multiply the probability times 2 to get this? Right? So if you didn't multiply it by 2, it would be less. Okay? Which is probably part of the problem. But the point of what I'm trying to say here is that when you have a one-tailed test, it doesn't really apply here, but in a one-tailed test, you can compare your test statistic to your critical value of z, just like you would compare a p-value to an alpha. So let's kind of write that together as a sentence. You probably should write it in your notes. You want p to be less than alpha and z to be less than z star. Okay? If either of these things happen, we would reject the null hypothesis. I'm telling you this because I have seen on AP tests in the past, mostly just with, I've seen questions written where they talk about the comparison of your test statistic to your critical value. So I wanted to just point that out, that that can happen and that that can be used to make a conclusion. I don't often rely on it because when you're talking about a two-tailed test, the p-value gets multiplied by 2. So it becomes a little different, okay? So I tend to only talk about this as a way to draw a conclusion. The p-value, I should write p-value, not p. Okay? The p-value should be less than alpha, which it did in this case because it was a two-tailed test. So you want to really stick with your p-value as your go-to. I'm just telling you because sometimes you're not given a p-value, and if it's a one-tailed test, you can still draw a conclusion. Okay? So that might be something you could see. Okay? All right, I just wanted to point that out. All right. Now, I'm a little hesitant to jump into the new stuff because it's very confusing, and I feel like we're already at a point where we are confused. So what I'd like to do is I'd like to try one more test as a class together from beginning to end to make sure we understand the process, we understand the steps, we understand what to look for, what to compare, and everything, and then we'll go into the new stuff. Okay? I really want to make sure that because the new stuff is confusing, and it can be. So I'm a little hesitant because I feel like we're a little nervous and uncomfortable at this point. Does that seem reasonable? Okay, especially since we've had snow days. So let's go ahead and try a problem. I'm just going to pick one out of the book, okay, for us to try together as a class. So if you need to borrow a book, that's fine. Let's try one that we haven't done yet. Tell me if we have done some of these or not. Yes, love? Because I had to add one of the tails in. Because if it's a Z star, the middle is 95%, which means each tail is 2.5%. So you add these two. So it's from here to here. 95 is the default. Yes, that's the default Z star, yes. All right, tell me if you've done this problem. I don't think you have. Have you done 26 for homework yet? Okay, let's do 26, okay? From the textbook in chapter 20. Let's do it together, okay? You can work together. I'm only going to give you about 5 minutes to do it from beginning to end, and then we're going to go over it, okay? So we should be at the point where we can do a complete hypothesis test in about that time. But I'm going to pause the recording for right now. Think about your 5 steps, check your conditions. But before you even jump into that, pick out your P, pick out your P hat, pick out your N, and go through the steps, okay? So I walked around and I saw a lot of really good things and a couple of little mistakes on quite a few of our papers. So let's just kind of make sure that we're doing the right numbers are where they need to be. Before I even begin my actual hypothesis test, I'm going to try to extract the information. I want to find what the claim is, what P is. I want to find what P hat is, which is our sample statistic, maybe a sample size, just so we know what is what. Very small. Very small in this case. So if I read question 26, we're talking about acid rain, and we're looking at a specific sample of trees called the Hopkins Forest. I'm not exactly sure where that is. Somewhere in the Northeast, I'm assuming in Maryland somewhere, I don't know. But we're looking at the study of effects of acid rain on trees in this particular forest. That's where we did our sampling, and it said out of 100 trees, 25 showed acid rain damage. So what would that be? What would this number be? P what? P hat. That's our sample. Very good. Okay. That's the number I collected from the forest. Okay. And I keep reading, and it does say that it seems to be a little higher than the 15% that was quoted in some sort of article that was on all trees in the Northeast. So the one that was quoted on all trees was about 15%. So what is that number? That's your P, okay? We want to see, is our sample different? Well, it doesn't say different. We'll look at what word it gives us here. Do I have evidence to suggest there's been a change from the quoted article statistic? So as I keep reading, by the way, N is 25. Would you agree with that? Oh, I'm sorry, 100. Oh, okay. Why not 25? What was 25 again? Okay, so that's actually the numerator. So the denominator of our P hats are N. Would you agree with that? Okay. I'm trying to show you different things that you can kind of connect to make sure you have them in the right place. So the denominator is your N. Good. All right. So let's go ahead and think. So I've extracted some key information, and I'll have to use that throughout my test. I think because I'm dealing with a proportion that I'm going to do a 1 proportion z-test, 1 sample z-test sometimes we call it. We're dealing with proportions. We've taken 1 sample of trees out of 1 forest. We're going to deal with 2 samples on Wednesday. All right, so let's go through. We've named our test. Let's write our hypotheses. So step 1 is to do our ho and our ha. They're always written in which, according to which one? P or P hat, Jordan? So it's going to be P equals what? 0.15. And what is the context of that? Okay, so we're trying to see whether or not our sample in Hopkins Forest is different than the claim. So we can actually say that There is no difference in Hopkins Forest. That would be an okay way to write the context in this problem as well. Rather than try to say the true proportion, because that's really talking about a confidence interval, a better way to say that would be Hopkins Forest really shows no different than the stated national average. Okay, so that's why I'm going to write it here. Our sample, Hopkins Forest, shows no different. Rather than that, I'll say Hopkins Forest has a 15% acid rain damage, whatever. Now, we know that our sample doesn't show 15%, but that doesn't mean our sample is completely representative of the whole population. We don't know. That's what we're doing a test to see. Now, the alternative, you have to read the question, and the question says, if you actually read the last sentence, it says, does the sample suggest that trees in the Hopkins Forest are more susceptible than the rest of the region? So is the proportion of acid rain actually greater than the rest of the region? And that's what we would say here. Hopkins Forest has more than 15% of acid rain damage. Okay? You need to tell me the hypotheses both in context and with the numbers. Okay? All right, step 2. What is it? Conditions. Good. We've already stated our test, so we don't have to do that again. Probably can put that there. The conditions. What do you think? It doesn't state that it's random. What can take the place of the random condition? Randomness is supposed to help us with what? Representative, right? We want our sample to be representative, okay? So if we don't have that it's random, we would have to assume that at least our sample was representative of all the trees in the forest, okay? Mm-hmm. What was the name of the forest? Thank you. Okay. All right, second condition. Got to use the numbers. So the number of our sample size in this case is 100, so we have to say 100 is less than 10% of what? And this is what Hunter and I were having a conversation about. All trees in the Northeast. Okay? Our sample size needs to be smaller than 10% of all the trees, not just of our particular forest here. In the Northeast is fine. Okay, and the third condition is going to be the success failure. Some people on their quiz simply wrote this and moved on. Had to take off. Why, this is the formula. This doesn't prove anything. So what would I have to do? Hunter, tell me what I would do. So it's 100, and it's P, which is 0.15, not the other one. So 15 is greater than 10. We've met that condition. And then the other one would be 100 times 0.85, which is 85, which is also greater than 10. Have I met the conditions? Assuming the first one is met, we'll assume, but we're okay. Okay? Step 3. Lindsay, help me with step 3. Okay, I'm going to go ahead and start with that, find the standard deviation. And here's a mistake a couple of us made. We know that it's PQ over N, but several of us wanted to do P hat and Q hat. We really always, if we have a claim, we're going to use that number here. We really only use the standard error when we're talking about a confidence interval, or if we're not really given a p. But we have a claim, so we're going to use the 0.15 and the 0.85 here. It's the standard deviation of my sample. This is still my sample. Okay? I see what it's a notational thing. It's still because we're still dividing by our sample size. Okay? All right, and I don't know what that number is, but we'll look at the book, and it tells me that it is 0.0357. Does that sound right? Good. Okay. Now what? Daniel, what do I do next? I got to find Z. Tanner, what's Z? What is it in just general terms? Z is a what? Test statistic, which we talked about just a second ago. And I know that it's going to be I like to draw them. It always helps me. 0.15 and then 0.25. We think it's greater than, so we're going to go here. So we know that our formula is 0.25 minus 0.15. And the Z, we should get a positive value, and I think we get 2.8. Okay? Good. Maddie. Where did the 0.25 come from? 25 out of 100. Okay? So when we're drawing our normal curve, the middle number when we're talking about proportions is simply the mean, which in our case for proportions it's your p, so it's 0.15. And then the other number is your p hat. And it's going to go to the right because it's bigger than 0.15. Okay? Good. All great questions. All right, what's my fourth step? Nathan, what's my fourth step? Okay, and how do I do that? So we're going to find our p-value. So I have my curve here to use, so let's do it. So normal CDF, and what do I type in? Some large number off to the right. Go ahead. That's our mean, which is? Good. Excellent. And that's going to be our p-value. I don't have to multiply it by 2 because it's not a two-tailed test. It's just a single tail. So our p-value in this case is going to be, they got 0.0026. Does that sound right to you guys? Way different number? You should never get a negative for a p-value. A p-value is always between 0 and 1. So let's do normal CDF. Hunter, look up here. The lower bound is 0.25. Okay, good. The upper bound is positive E99. The mean is 0.15, and then the standard deviation is 0.0357. Yeah, I got 0.0022. I mean, mine's probably off because why? The standard deviation was rounded. Okay, but it's awful close, wouldn't you say? Good enough. All right. What's my last step? Step 5. I have a draw conclusion. There's 2 ways I know how to do it now. I can compare my Z to my Z star, or I can compare my p-value to my alpha. The alpha, I don't think it gave us anything to say here at a certain level, so we'll assume 0.05, okay? So we're going to say that 0.0026 is less than 0.05, therefore what do? I reject that bad boy, okay? I reject the null, which means that the likelihood that my sample happened by chance is real small, which means that the trees really are messed up by acid rain, okay? Which means that we're going to reject this and say that we have evidence to suggest, and it's fairly strong evidence because the p-value is pretty small, isn't it? Okay, so we have relatively strong evidence to suggest that more than 15% of trees at the Hopkins forest are damaged by acid rain. So we have strong evidence to suggest that more than 15% of trees in Hopkins forest are damaged by acid rain. On a future test or quiz, much like you had to do on your quiz, you will have the quiz you took before the snow. You'll have to do a 1PropZ test from beginning to end. Okay? Now, how do I check it on the calculator? Let's refresh that. I don't think many of us did that on the quiz. How do I do that? Where do I go? Do you remember? Stat test. 1PropZ test, which is option 5. Let's plug in the information. What's that P with a 0? That's your claim. So what is that? 0.15 here. And then we're going to put in our proportion. So it'd be 25 out of 100. And we're looking to see that it's greater than, which is the last option, which is the one that's highlighted. So remember, we can draw it too if we want to make sure that we have it drawn correctly. Oh. Sorry. There's a thing on there. Hang on. I'm going to take this little dude out. Clear. Sorry. I don't want it to distract us. What did it do? Sorry. I think I have to go back and do it maybe. All right, let's try it again. Huh. I don't see anything shaded. Why? You have a question? You're going to answer my question. I can't understand you, sweetie. I'm in the middle of a discussion, so if it's an emergency, just I trust that you can go ahead and handle it. I agree with you. 2.8 is really way down there, okay? It's a pretty large z-score, which means that it's probably not going to show up as shaded very well. And the p-value is very small, right? So it's not going to, it probably won't show a lot that's shaded. But we do have an information that we need, so that was good. Okay? 2.8 was our z, 0.0026 was the p-value. We look good. Do you feel a little bit better going through one more from beginning to end, Lena? You sure? Okay. Maddie? A little better? The more you do, the better you're going to get. My concern is that every single thing we do from here on out is building on this one test. You've got to understand what each of the pieces are, because every other test is going to add more to it, more to it, and more to it. So I don't want to move on until we understand this. It's because you have something in your y equals that is prohibiting it from doing that. Your plot 1 is turned on. Turn your plot 1 off. Then it should work. Try it again. Let me know. Okay. Anything else we need to talk about? Sure. I knew it would. All right, ready? All right, folks. I need us to stand up. We only have 25 minutes, but I'm not going to, which is probably good, because it's not going to, I'm not going to get to everything that I wanted to. Stand up, stretch for a second. Stretch your brains. Do anyone need a dum-dum, a little sugar? You got 30 seconds. All right, so we've already decided what a p-value is, but I'm going to go ahead and bring it back up, because what we're going to talk about for the rest of class, which isn't that long, is what are called type 1 and type 2 errors. Whenever you collect a sample, okay, we know that there can be errors in the way that we collect them. And the p-value that we get can help us in determining some of those errors. Okay? So let's just remind ourselves. One way to define a p-value, okay, is the probability that the observed statistic, the observed, what we collected, given that we're saying the null hypothesis is true. Okay? It's a different way to say interpret a p-value. Same thing we've done all along, but a p-value is just it's a probability. It's a probability that our sample happened, assuming that our null hypothesis is a true statement. Now, the null hypothesis may be true, it may be false, okay? But we're going to say that the p-value is assuming that that's going to be a true thing. Okay. Oh, we already know what this is, sorry. We know this. Okay. So, hang on. Oh, here we go. This is what we need to know. What is a type 1 versus a type 2 error? So these are like the definitions of them. A type 1 error is actually a pretty easy error to figure out. It's always going to correspond to our confidence, or our alpha level. So often it's 0.05, okay? A type 1 error is when you reject the null hypothesis, but it's actually a true thing. We shouldn't have rejected it. So it's an error because the p-value that we got told us to reject it, told us that we're going to reject the null. That's the information according to our hypothesis test. The p-value was low enough where we could reject it. However, we shouldn't have because it was a true statement. So it's called an error. And they happen. So I want you to highlight or to write down this information because this is what you need to know. So the first error is when I reject something that I shouldn't have. Okay? Just put it on my desk. A type 2 error is a little bit more complicated. A type 2 error is when I don't reject it. I fail to reject it. But it actually was false, and I should have. Sort of. I hate to say opposites, because opposites usually mean complements, and they're not complements, but they do affect one another. Okay? So, no, because you can have both. Oh, no, I said it wrong. We are going to find probabilities of the type 2 error, so the probability of one happening will affect the probability of the other happening. You can't reject and not reject. That's not what I meant. But the probabilities are related to each other. The probabilities are not complements necessarily, but they are related and do affect one another. You going home? Okay. Feel better? Okay. So, I will say for the most part, not always, but most often, a type 2 error has a greater impact. A type 2 error is probably most often more horrific. It's a worse error to have. So I'm going to put a star by it. Well, maybe I will. A star by it, because usually it has a bigger impact. So it's a worse situation.
When you say it's a worse situation, it means like in the context.
In the context of the problem. So we're getting ready to look at that, okay? So you'll see what I mean. Okay? Can I move on to the next page? Do you have this written down? It'll be on School Fusion. So here is a scenario. You don't have to write this down if you don't want. You can print them off at home. I'll put them on School Fusion. But let's go ahead and look at, and I apologize for the placement of these letters here. I'm not sure what is going on with those, but we'll try to read the best we can. So research into the effectiveness of a new drug. We want to slow the growth of tumors, used a following hypotheses. So we have a null hypothesis here. We have an alternative hypothesis here. Okay? The null hypothesis says, do you have a early dismissal class?
She said she was going to send it like 10 minutes ago. Can I go to her?
Who is it?
The third floor office.
No, because I mean, I'm in the middle of teaching a class, Danny. Let me just check my email. I haven't gotten anything. You can go get a pass, bring it back to me. Okay. So the null hypothesis says that the proportion, okay. I'm not even sure what that's supposed to say. Let's look at the alternative. The proportion with growth in tumors is less than that without a treatment. So less than, okay? The proportion doesn't change. There's no change, okay? So I'll just write no change in the drug. The drug does not affect the growth, okay? And this one is that the growth shrinks with the drug. We good with what I'm saying in terms of the context? Okay. Let's describe the type 1 and type 2 errors in context. So, type 1 error is when I reject the null when I shouldn't have, when it's true. So the type 1 error in this case is going to be that I reject it. I say that there's no change in the drug does not affect the growth. But it does. Does that make sense? Let me say that again. So look, we reject the null when it's true. Okay, we reject the null. We say we reject the null, but it's true. So the null hypothesis in this case says there's no change. So we say the drug is effective. We reject the null. We said it's effective, but it's not. Do you see what I'm saying? So this would be in the context of the problem. We reject the null, therefore we say that the drug is effective, but it's not. The evidence we had was a p-value that was small enough to suggest that the null was not true. We had evidence to say that it was less than, so the drug was effective, but it's not. What would be the ramifications? What would be the problem? What would be the situation? What would happen if we did this? If we as statisticians told the drug company that the drug is effective, but it's not? Amanda? Patients would be taking more drugs, wouldn't they? They would be taking drugs that didn't work, right? And so that would be a problem. There could be side effects, there could be things that happened, right? So that would be a problem. What would a type 2 error in this situation be? So let's remind ourselves what a type 2 error is. It's when we don't reject the null, but it's actually false. So what do we say in this case? We say the drug is not effective, but it is. What would be a result of a type 2 error or that type 2 error? Yes, you can. Well, people are dying and they didn't need to, right? We found something that worked, and they're not able to take it because we had bad stats, right? We told them wrong. We had a type 2 error. Do you see how that's really a worse problem than a type 1 error? Oftentimes that happens. All right? So let's do another one. We're going to practice this, and your homework is going to be to read the chapter, and you're going to be assigned describing type 1 and type 2 errors. And we're going to talk about how to find those probabilities and stuff on Wednesday. So how about this one? we're creating or we're testing a sensor to test for explosive devices. We placed 4 boxes. One has explosives in a room, and figure out this test to see if it identifies the correct box. Why is the null that? Because 1 out of the 4 actually has the defective, right? Or has the explosive. So that's why. Why do we want the alternative to be that? Okay, we want to make sure that it wouldn't be less than, right? We want it to be at least that. Would you agree? It's okay if it's a little bit more. It says 2 have it and they don't. That's okay. All right, so what's type 1 error in this case? Remind me what a type 1 error is again. If we need to go back to read it, we can. We reject the null, but it's true. So we reject this. We say what in the context of the problem? Okay, let's think about this. Well, we actually don't even have to be specific about the 1 box thing. We can just say, does the test work or not? We say it works and it doesn't, or we say it doesn't work and it does. Which one's happening here? I don't know. I'm asking you. So in this case, we're going to reject the null when it's true. We're going to say that the test works, but it actually doesn't. There are, like I said, sometimes there's one that's a little odd. Okay? So again, it depends on the context of the problem, but most often a type 2 is worse. A type 2 would be, okay, so let's just double check. So what's a type 2 again? Is when we don't reject the null is true, okay, but it's in fact false. So in this case, the test doesn't work, but we say it does, okay? So we say the test works, but it doesn't here. We say the test doesn't work, but it actually does. Okay? And Charles was like, well, in this case, which one's actually worse? Okay, in this case, you're right, it doesn't detect the problem. Okay? So we have to think about that. Let's make sure we have that as the right hypothesis, though. I'm a little concerned with the way that is. So again, a type 1 is when let's double check it, we reject it when it's true. So we're going to say, oops, sorry, we're going to reject this when we shouldn't have, right? So we're going to reject it. We're going to say that it does work. That's right, but it actually doesn't. Okay. All right, so your homework is just going to be to identify type 1 and type 2 errors in a specific context, okay? And to read chapter 21, and then we'll finish up the chapter on Wednesday. So chapter 21, you must read it. Please read it all, okay? I don't know yet. We'll have to see what we do on Wednesday. Okay? I might make it Friday and just take something off. I might take the 2 proportions off. I'll have to we'll make that decision Wednesday. But anyway, read chapter 21, sorry, and then let me pick problems that are just with identifying. Give me 1 second, sweetheart. All right, so definitely read the chapter, and then I want you to okay, starting with problem number 11. All right, just 11, 12, and 13 is really all this would be. So let's do 11, 12, and 13, and the just checking. Okay, so that together will be 1 homework assignment, and then I will also check for the one that was due today on Wednesday. So both of those will be due on Wednesday. Fair enough? Okay.